I want to show you this cool demo, and I've seen it at other places too. So I have two carts. This one's much heavier than that one. They're not even the same brand, and you can do that, that's fine. And it's on a track that's mostly balanced by these two Lego pieces right here. So just so you can see that if I tilt it, see, it's not completely stable, right? And so you got to get this thing just in the middle right there. Now I have a spring plunger that will push them apart, and then I have a rubber band that will prevent them from getting too far apart. So when I do that, the red card is going to go this way. And it's hanging over the edge. You can see right here what's going to happen. Okay, let's do it. Okay, so it did tip at the end, but it didn't tip at the beginning. So what's going on here is that there is a force pushing on the red car, and it does move that way. But that same force pushes back on the heavier car, so it also moves. And in fact, we like to think about this in terms of change in momentum. They have equal and opposite changes in momentum because they have equal and opposite forces. That means that the center of mass of the system has no forces on it. It's only an internal force, so the center of mass doesn't change. This heavier cart does indeed move back, not as far, but that actually just makes the center of mass stay right at the center. And then when the cart gets over here, the rubber band is also a force, an internal force. It does not change the center of mass. So why does it actually finally tip over? Well, it's because there is some external force on this, and that's from friction. So the frictional forces between these and the track eventually change the center of mass so that it tips over a little bit, and that's what happens. So if you had a perfectly frictionless thing, it would be perfectly perfect.